Is it possible to build a light-speed spacecraft using the technology that we have available to us today? Now, this might seem like a silly question, but bear with me. The most significant limiting factor to space travel by far is the cost to orbit, or the cost to get stuff into space. So this got me thinking, say we had an unlimited budget, how fast could we realistically go with the technology that we currently have available to us? Well, today we're going to go through all the options and the math. We're going to work this out, but don't worry, you don't need to be a math whiz or a rocket engineer to follow along. I'm going to lay it out in as simple and super easy to understand way as possible. So the first question might be, why light speed? Well, our current understanding of physics is that faster than light speed travel is impossible according to Einstein's theory of special relativity. So the theoretical highest possible speed that we can travel without breaking or bending special relativity is just slightly less than light speed. Now the speed of light, get ready for this, is 299,792 kilometers per second. Let that sink in for a second. Now, for the sake of simplicity in this thought experiment, we're just going to round that up to 300,000 kilometers per second. Now, for reference of how fast that is, the moon is at its closest point to Earth about 363,000 kilometers away. So at light speed, we'd be able to travel from the Earth to the moon in 1.2 seconds. That's pretty quick, obviously, but say we want to aim for something a bit more ambitious, like for instance, the nearest Earth-like planet that we're currently aware of, that would be Proxima Centauri b, which has a pretty similar gravity and possibly even atmosphere to the Earth. Now, Proxima Centauri b is 4.2 light years away from Earth, so traveling at the speed of light, it would still take 4.2 years to reach. So the point here is, if we really want to get anywhere cool in our galactic neighborhood, so to speak, we need an ultra-fast spacecraft, and light speed is sort of the current speed limit as far as we're aware in our universe. So we've established the what and the why. Let's get to the how and actually build this thing. I'm going to put a caveat on this though. There are obviously many engineering challenges to this outside of just the propulsion methods. There's the deep space low gravity, the radiation health risks to the crew, there's challenges like designing heat shields to protect the ship from near-sun gravity assists, which we'll talk about later, as well as a whole host of other technical elements. But to save this video from becoming 7 hours long, we're going to assume that all these problems have been solved and we're just doing the propulsion system. And we're also going to assume in this thought experiment that we're going to build this craft in space, as it saves all the calculations of actually getting all the stuff into orbit, and realistically it'd be far more practical doing it this way anyway. We actually have quite a few propulsion methods available to us. I'm going to go through them one by one, starting with the most common and simple, and we'll work our way up to the more advanced and exotic methods. Now, bear with me for a little bit because we need to do a little groundwork first to set the stage. First up, we need to establish what we're looking for in the ideal propulsion method. Now, if you're anything like me, your first thought might be, well, let's just go for the brute force method. We'll fire a giant starship into orbit with a massive fuel tank and say 500 SpaceX Raptor 3 engines. We can work out the maximum speed, or delta V, meaning change in velocity in rocket terms, of this spacecraft using the Tsiolkovsky rocket equation. Without getting too into the maths of it here, basically the Tsiolkovsky rocket equation can help us work out the maximum theoretical speed of a spacecraft. So plugging the numbers in here, our 500 Raptor 3 engine powered spacecraft comes in at a maximum delta V, or speed, of 7.9 kilometers per second, or in other words, 0.0026% the speed of light. Yep, that's it. Okay, brute force, let's just add another 500 Raptor 3s. Surely that will make it faster. We plug those numbers into the Tsiolkovsky rocket equation and we get the exact same number. How does that make any sense? The issue here is the exhaust gas velocity, or probably better expressed as specific impulse, or ISP. Now take note of that. We're going to be talking a fair bit about ISP throughout this video. Now ISP, which is measured in seconds, is essentially the efficiency of a rocket engine, which is determined by the exhaust gas velocity. The idea of a rocket engine in its most basic form is to shoot as much stuff, gas, out of the exhaust as fast as possible. Now ISP, or specific impulse, is different to thrust. Simply put, the more gas that exits the nozzle, the more thrust is generated. but the faster the gas is traveling when it exits the nozzle, the higher the ISP. Now, bolting more Raptor 3 engines to our craft increases the thrust, but not the ISP. This is because all the engines have exactly the same ISP, so bolting more of them on doesn't actually increase the exhaust gas velocity of each. Now, this isn't a perfect analogy, but think of a car traveling on a straight road. The car can't go faster than the speed the wheels are driving it. It doesn't matter how much horsepower you add, if the wheels aren't spinning faster, the car will not go faster. Now, I'm not ripping on the Raptor 3. Keeping with the car analogy, Raptor 3 is built for power, not so much speed. It's built for thrust, but not super high ISP. Generally speaking, higher thrust rocket engines don't have a super high ISP, and high ISP rocket engines don't generally have a lot of thrust. Now, for breaking away from the surface of the Earth, you want high thrust. But for traveling at high speeds in space, what you want is high ISP. Okay, so all this considered, what chemical rocket engine would be a better choice for our application than the Raptor 3? Now, currently, the Aerojet Rocketdyne RL10 has the equal best ISP of all chemical rocket engines at up to 470 seconds in a vacuum or in space, compared to only 350 seconds from the Raptor 3. Now, the RL10 runs on hydrolox, hydrogen and oxygen, where the Raptor runs on methalox, being methane and oxygen. The reason I bring this up is lighter fuels tend to have a higher ISP. Now, as hydrogen is lighter than methane, the hydrolox-powered RL10 has an ISP advantage over the Raptor. Now, one of the great things with the RL10 for the purposes of this thought experiment is we actually have really good real-world numbers we can draw from based on the several interplanetary missions the RL10-powered Centaur upper stage has performed. Okay, let's get back to our ship. Now, since we know it doesn't matter how many chemical rocket engines you bolt on, the maximum speed will be limited by the ISP, not the thrust, and adding more engines increases the thrust, not the ISP. Let's go with the Centaur upper stage I mentioned earlier as a basis to work from. Now, it has 2 RL10 engines. So we plug the numbers back into our Tsiolkovsky rocket equation. We end up with a max delta V, or speed increase, of 10.1 kilometers per second. Now, it's important to note that this is just the additional speed added by the RL10 engines. We're already going to be in orbit when we fire these engines up, so we can go ahead and add the orbital velocity we're already carrying of 7.8 kilometers per second, as well as assuming we're also going to use the Earth's velocity around the Sun to our advantage, or essentially the speed we're traveling around the Sun. We get a maximum speed of 36.68 kilometers per second. Now, that's not bad, but it's a far cry from 300,000 kilometers per second to get to light speed. So we've essentially exhausted all of our chemical rocket engine options, and we're currently at 0.0122% of the speed of light. Now, you might be thinking our next step here is going to be more exotic engines such as nuclear propulsion, ion thrusters, etc. But before we get there, there is a much simpler method we can use to increase our speed. I mentioned earlier in the introduction, gravity assists. Now, the Sun obviously has the strongest gravitational field in our solar system, so it's going to be the best candidate for a gravity assist. Now, to get the biggest gravity slingshot effect we can from the Sun, we're going to have to perform a perihelion maneuver. Now, a perihelion maneuver is essentially a dive at the surface of the Sun. The closer you get to the surface, the greater the slingshot effect. This is actually the maneuver the Parker Solar Probe, aka the fastest traveling object humans have ever made, used to slingshot to its maximum speed of 192 kilometers per second. Now, as I mentioned at the start of the video, we're going to assume that we've been able to solve the engineering challenges associated with the heat and radiation from a very close pass of the Sun, so we can get the maximum slingshot effect from our perihelion maneuver. Now, theoretically, a delta V, or speed increase, as we discussed earlier, of 600 kilometers per second is possible from a very, very close pass to the Sun. Now, to reach this delta V, we'd be passing within 73,000 kilometers of the Sun's surface. That might seem like it's still a very long way away from the Sun, but even at this distance, our poor little spacecraft would be experiencing temperatures exceeding 5,000 degrees Kelvin, about 4,720 degrees Celsius, or 8,540 degrees Fahrenheit. Now, for reference of how hot that is, during re-entry, the highest heating experienced by the space shuttle was on the carbon composite nose cone, which reached a maximum temperature of 1,650 degrees Celsius. So yeah, 4,720 degrees Celsius is pretty hot. So hot that there's no known substance that wouldn't be vaporized instantly at this temperature. Now, if our ship survives that though, we get the trade-off of an additional 600 kilometers per second delta V boost. So, all good. Now, in theory, we could perform the same maneuver multiple times to increase our delta V. However, the rule of diminishing return applies here. So each pass will achieve less and less increase to our delta V. I think we're well and truly pushing the limits enough with one close dive at the sun. So let's leave it at one solar gravity assist. So with our original velocity of 36.68 kilometers per second and the 600 kilometers per second solar slingshot boost, we're now traveling at a blistering 636.68 kilometers per second, or 0.2124% the speed of light. Yeah, that's it. How long at this speed will it take us to reach Proxima Centauri b? The answer is 1,996 years. Okay, so now's probably the right time to have a look at some of those more advanced exotic forms of propulsion. Now, before we do, if you're enjoying this video, do me a favor and hit that like and subscribe button if you haven't already. I have a heap of awesome content on the way, and trust me, you won't want to miss it. Now, since we're on the topic of the sun, probably best to get solar sails out of the way. Now, if you're unfamiliar, solar sails are pretty much exactly as advertised. They're incredibly thin, large surface area sails coated in a reflective coating, which is designed to catch photons coming from the sun. Now, even though photons have no mass, weirdly, they exert a very small amount of force against the sail when they bounce off, producing a thrust-like effect. Now, another weird quirk of solar sails is they technically have an infinite ISP, sort of, because they don't technically use fuel as such, so they're infinitely efficient. Now, the drawback of solar sails, and the reason they won't be unfortunately useful on our light-speed spacecraft, are twofold. Now, while solar sails are ultra efficient, the thrust effect they produce is incredibly low. The solar sails produce a thrust of 0.000000908 newtons of thrust per square meter of sail. So let's say you had a solar sail with a surface area of 100 meters squared, to make it easy. This would only produce a thrust of 0.0000908 newtons. Now, for reference, each of the two RL10 engines we have on board produce 66,700 newtons, or 66.7 kilonewtons of thrust. So to have any noticeable effect, our solar sails would have to be absolutely enormous. The second major drawback of solar sails for our ship is, as solar sails work by catching photons from the sun, the further away we get from the sun, the less photons they're able to catch, and the less thrust they're able to produce. Now, as we're planning on a deep space interstellar trip, solar sails will be rendered useless for the vast majority of the journey. So solar sails are unfortunately a no. So now we can finally get to the more sexy, exotic forms of rocket propulsion. Now, straight off the bat, I'm sorry, but we're not putting fusion or antimatter propulsion systems on our ship. Now, we will talk about them later, but these are theoretical only and they've never been tested, so they don't quite fit the bill of technology we currently have available today. Don't worry though, we still have some really cool high ISP rocket engines on the list. We're going to briefly touch on each one, then pro-con them all together at the end to work out which will be best on our light-speed spacecraft. Now, the first one we're going to talk about is NTP, or nuclear thermal propulsion engines. Now, these are different to NEP, or nuclear electric propulsion engines, which we'll get to in a minute. So NTP engines, or nuclear thermal propulsion engines, are a kind of really high-tech version of a low-tech idea. Now, the simplest way I can explain this, think of a steam locomotive. Now, inside the locomotive is a coal fire, which heats water in a boiler, producing high-pressure steam. This high-pressure steam is then used to turn the engine. Now, another higher tech version of this same idea is used in military nuclear submarines. Instead of a coal fire, these use a nuclear reactor to generate heat. Heat is used to boil water into high-pressure steam, which is used to turn a turbine and produce power. Now, an NTP rocket engine essentially uses this same base concept. It uses a nuclear reactor to generate thermal energy, or heat, which it then uses to heat cryogenic hydrogen. Now, the heat pressurizes the hydrogen, which it then directs into a converging diverging nozzle, essentially a rocket nozzle. Now, the converging diverging nozzle converts the high pressure, low speed hydrogen gas into low pressure, high speed hydrogen gas exiting out the nozzle. Now, NTP rocket engines are capable of an ISP of up to 1,000 seconds, which is more than twice that of an RL10. Now, you may ask, how can an NTP engine produce twice the ISP of an RL10 when they run on the same fuel source, mainly hydrogen? Now, the difference primarily comes down to the composition of the exhaust gas. Now, an RL10 runs on hydrogen and oxygen. So when they combust inside the engine and exit the exhaust, they become water vapor or H2O. Now compare this to the exhaust of an NTP engine. As no actual combustion has taken place inside the NTP engine, the exhaust gas is pure hydrogen. And we know from earlier that lighter fuels tend to have a higher ISP, therefore an NTP engine with its pure hydrogen exhaust gas is going to have a higher ISP than a Hydrolox engine with its H2O exhaust gas, or at least it has the potential for a higher ISP. I hope that makes sense. Again, I know there's slightly more going on here, but this is essentially the crux of it in its simplest form. Next, we get to NEP engines, or nuclear electric propulsion, and ion drives. Now I'm going to group these two together, NEP and ion drives, because they more or less function in the same manner, but just use different sources of electrical energy. Now, if this starts to go a little over your head, don't worry, I promise it will all come together in the end. To explain NEP and ion drive engines, we're going to have to touch on the electrical charge of atoms. Now, NEP and ion drives use xenon as a propellant. Xenon is one of the noble gases, meaning it's totally unreactive, making it very safe and stable to store. It also has a neutral electric charge. Xenon has 54 protons and 54 electrons. Protons are positively charged and electrons are negatively charged. As the numbers of each are equal in a xenon atom, it has a neutral overall charge. Now, NEP and ion engines work by bombarding xenon atoms inside an ionization chamber with electrons from a hollow cathode. Now, when these electrons collide with the xenon atoms, they strip away or sort of bump off one or more of the xenon atom's electrons. Now, as it has now the same number of protons, but now less electrons, it becomes a positively charged xenon ion. Now, ionization is essentially the process of stripping away or adding electrons to the atom, hence where the ion engine gets its name. Now, at the end of the ionization chamber are two electric field grids. In much the same way that a magnet attracts and repels other magnets, the two electric field grids attract the positively charged xenon ion and then expel it from the exhaust of the engine at an extremely high speed, producing thrust. Now, if that went over your head, the short version of that is NEP and ion drive engines essentially use electricity to shoot xenon atoms out the exhaust of the engine at super high speed, giving them a super high ISP, generally between 8,000 and 10,000 seconds. Now, there is still significant progress being made in this area. The DS4G ion thruster, or dual stage 4 grid, developed by the ESA, European Space Agency, and the Australian National University, which is a rare space win for Australia, attained an ISP of 19,300 seconds when tested in a lab. So clearly we still have some significant room for development on this front. Now that we hopefully have a basic understanding of ion propulsion, what is the difference between NEP and an ion drive? Now, the ionization process requires electricity to function. An ion drive typically generates this power by use of solar panels, whereas NEP generates electricity using a nuclear reactor. Now, for the same reason that solar sails aren't appropriate for our interstellar spacecraft, the solar power needs of the ion drive aren't going to be appropriate. So NEP is going to be the clear winner here. The other factor is the nuclear reactor to power the NEP engine can also provide heat, life support systems, and more importantly, electricity for basically every system on the spacecraft quite easily. So that's a pretty clear win too. So now we've covered our advanced high ISP rocket engine options. Which one should we go for? Now, as we discussed at the start, for speed in space, ISP is king. Now, our NTP engines have a significantly lower ISP than the other options we've talked about, so they're out. So now we're left with ion drives and NEP. Now, because ion drive engines rely on solar, which we won't have as we travel away from the sun out into the galaxy, we're going to go with the NEP engines. So back to our spacecraft. Now, that was a lot of info, so just to refresh. With our RL10 engines, the full exploitation of a delta V advantage from both our low Earth orbit and the Earth's orbit around the sun and the perihelion slingshot maneuver we've performed around the sun, we're currently at 636.68 kilometers per second, or 0.2124% of the speed of light. So let's bolt on our super advanced NEP engine. And we're going to use the lab tested numbers from the DS4G thrusters, as these are real world numbers, even if not technically achieved in space. We plug these numbers as well as our current speed back into our Tsiolkovsky rocket equation, and we get a maximum theoretical delta V, or speed, of 1071.8 kilometers per second, or 0.3575 of light speed. So at this speed, how long will the trip to Proxima Centauri B take now? 1,186 years. Well, we're moving in the right direction at least. The NEP engine has shaved 810 years off the trip, so that's not bad. Now, you may fall back into the thought trap of let's bolt 50 more NEP engines on and enough fuel to fire them all for 100 years. This is, of course, the same thought trap we fell into with the Raptor engine. No matter how many NEP engines we have, they're all going to have the same ISP, and ISP is a limiting factor. So once again, the car cannot go faster than the speed its wheels are driving it. Now, by adding more engines, we're only increasing thrust, not ISP. Now, interestingly, because of the incredibly high efficiency of the NEP engine, even at only 1 Newton of thrust, we'd actually only need to fire the engine continuously for about 20 days to reach its maximum delta V. If we were to continue firing the engines after this 20 days, we're essentially just wasting fuel. We're not traveling any faster. I really didn't want to have to pull this one out, but we don't have any other options, so nuclear pulse propulsion. Now, nuclear pulse propulsion, or NPP, is a theoretical method of propulsion that involves using controlled nuclear explosions to generate thrust. Now, if you're not familiar with NPP, yes, it is exactly as advertised. Eject and detonate nuclear bombs behind your spacecraft to propel you forward relatively speaking, in the direction you want to go. Now, the design incorporates a pusher plate or blast plate, which would be connected to the spacecraft by shock absorbers to reduce the mechanical stresses on the vehicle from the waves of extremely high velocity plasma caused by continuous nuclear detonations. Now, I really dislike this concept. Compared to other options, it's so inelegant. Like, let's blow up a nuke behind our spaceship and that'll make it go so fast. Like, it sounds like something from an early 2000s straight to DVD, low budget sci-fi movie. Now, what's even more frustrating is that in theory, it works. Of all the super advanced propulsion methods we've talked about so far, this one is by far the most powerful, most efficient, and really the only method that has any hope of getting our spacecraft up to a significant percentage of light speed. Now, this idea was first developed as part of Project Orion by DARPA, which is the Defense Advanced Research Projects Agency of the United States, in the 50s and 60s. So the idea has been around for a while. So the important part, how fast will our spacecraft go if we incorporate an NPP drive? Well, we go back to our Tsiolkovsky rocket equation. We obviously have quite a bit of data on the yield of nuclear bombs from the many tests that have taken place since the early 40s. Several of which were detonated in space, including the infamous Starfish Prime test. Now, obviously, detonating a nuclear bomb behind a spacecraft isn't quite the same as firing a rocket engine, but we can still get an effective ISP. Now, the exhaust gas velocity, or in this case more accurately the plasma blast velocity of a nuclear fusion bomb detonated in the vacuum of space, would be up to an average 3,000 kilometers per second, giving us an ISP of around 300,000 seconds. Now, keep in mind, because this is purely theoretical, there's a pretty wide variation of estimates due to there being many variables. So I'm doing my best to average and round things out slightly down to be conservative. So just to refresh your memory, the DS4G ion thruster we last bolted to our spacecraft had an ISP of 19,300 seconds. I'm no mathematician, but 300,000 seconds is a lot more big than 19,300 seconds. 15 and a half times more, actually. As frustrating as it is to say, looking at these numbers, I've probably judged nuclear pulse propulsion a little bit too harshly, to be honest. So, how fast can we go now? We're currently traveling at 1,071.8 kilometers per second, which is 0.3575% the speed of light. So let's say we bolt on our MPP drive, we load up 1,000 bombs and spread the detonations over a 10-year period. Now, at the end of that 10 years of firing our NPP drive continuously, we are traveling 47,061 kilometers per second, or 15.7% the speed of light. Now, at that speed, how long is it going to take us to get to Proxima Centauri B? 27 years. All right, but can we scale up our nuclear pulse propulsion and use more bombs for more speed? Or do we run into the same issue as with the other forms of propulsion we've tried this with? Now back to the Tsiolkovsky rocket equation one more time. And the answer is yes and no. We are still limited to a maximum speed dictated by the ISP, as with every form of propulsion, but 1,000 bombs isn't enough to reach it. We can actually squeeze a bit more juice out of it. With 2,358 high-power fusion bombs, we would be able to reach a maximum theoretical speed of 68,952.2 kilometers per second, or 23.4% the speed of light. Now at this point, we'd get our spacecraft from Earth to Proxima Centauri B in only 18.1 years. That's doable, right? Now it's been fun working all this out, considering each of the propulsion methods available to us, but I have some simplifications I'd like to make to the spacecraft, knowing what we know now. Firstly, we're going to ditch the NEP engine and the solar gravity assist, as with nuclear pulse propulsion, they're both redundant. Now we are going to keep the RL10 engines though. We're going to use them to break out of Earth's orbit, align our trajectory with Proxima Centauri B, or more accurately, where it will be by the time we get there, because remember, we're not stationary in space, and neither is Proxima Centauri B. We're going to get some distance between our spacecraft and the Earth before we light up our NPP system, because if you're familiar with the Starfish Prime test I mentioned earlier, you'll know that detonating a nuclear bomb in near-Earth orbit isn't the best idea unless you're planning on destroying every single satellite currently in orbit with a massive EMP burst. By the way, if you haven't looked into the Starfish Prime test I've talked about a couple of times now, it's worth looking into. It is super interesting. Now the other modification I'd like to make is the addition of control thrusters that are powerful enough to flip our spacecraft 180 degrees around for deceleration. And obviously storage of another 23,058 nuclear bombs, which we can use to slow our craft back down once we get to Proxima Centauri B. There's obviously no point traveling 4.2 light years across the galaxy only to slam into the destination planet at 252,544,780.8 kilometers an hour. Now there is one more complicating factor here, and that's G-force. Now we humans are pretty fragile, and high Gs don't really agree with this. Remember, the crew will have to endure the acceleration Gs as well as the deceleration Gs, which from their perspective in the ship will feel the same because we're going to be doing a flip maneuver halfway to decelerate. Now if we detonate our 2,358 bombs over 10 years, assuming the pusher plate does a pretty effective job and smooths out the force from each explosion somewhat, what will the average G-force experienced by the crew be over the period of the trip? 22.8 Gs. Not survivable. Most humans can endure 4 to 6 Gs over a very short period of time. So realistically, we'd unfortunately have to spread the trip out around 45 years to keep the average under 5 Gs. And even that is really pushing human physiology. And remember, that's just to get the ship up to speed. Then we have to spread the deceleration across 45 years as well. So we're definitely going to have to make some progress in that arena. What technology do we have to invent to go faster than 23.4% the speed of light, or the maximum speed that we can get with our NPP drive? Now, I mentioned fusion and antimatter drives earlier in the video. And as I said, they are currently a theory only and no proof of concept currently exists. Now, that doesn't mean they're both equally far away though. Now, fusion drive may actually just be around the corner. There are currently, as of the time of writing, 3 active fusion drive projects currently in the works. Now, unsurprisingly, NASA is one of them with their FDR fusion-driven rocket project. Very creative name there. Princeton Plasma Physics Laboratory with their DFD direct fusion drive, and UK-based Pulsar Fusion with their direct fusion drive. Now, the latter of those, Pulsar Fusion, has stated they're aiming for an in-orbit demonstration in 2027. The predicted ISP ranges from 10,000 to 15,000 seconds, so nothing game-changing at first, but Remember, if successful, this would be the first fusion engine ever built and demonstrated, so think of this more as a proof of concept. The maximum theoretical ISP of a fusion drive engine is 1.5 to 3 million seconds, which obviously is far higher than an NPP drive, so there's obviously a lot of room for advancement there, and that's really exciting. Now, on top of that, as this would be constant acceleration, not pulses, we can actually accelerate a lot faster without harming the crew and not have to spread it out over such a long period of time as with NPP. Because the acceleration would be linear as well, not pulsed, we'd be able to thrust the engines in such a manner as to provide the closest thing to artificial gravity. At the halfway point, just flip the ship around, similarly to what we decided we'd do for the NPP system, and decelerate the ship at the same rate, providing the same artificial gravity effect. Now, it'd be less than a full 1G, depending on the length of the trip, as accelerating continuously at 1G would end with you traveling over light speed in less than a year. But even, say for instance, 0.2G or 20% of the Earth's gravity would make a significant difference to the health and comfort of the crew. Now, antimatter propulsion, however, is a different story, unfortunately. But that being said, the more I look into it, the more optimistic I am about it becoming a reality in our not too distant future. Now, explaining how a fusion drive works is far too complicated for a video that's already too long, but antimatter propulsion is a fair bit easier to explain quickly, so I'll give it a go. Now, antimatter is pretty much as described. It's essentially negative matter in simple terms. When an antimatter particle comes into contact with a matter particle, they convert their mass into energy in a process called annihilation. Now, this energy comes in the form of gamma rays and charged particles, pions, muons, and neutrinos. The energy released from this annihilation is immense. 1 gram of antimatter coming into contact with 1 gram of matter releases an amount of energy equivalent to 43 kilotons of TNT. Now, to put 43 kilotons of TNT into perspective, the little boy bomb, the fission bomb that was dropped on Hiroshima, had a yield equivalent of 15 kilotons. So 43 kilotons, it's like 3 times that. It's quite a bit. Now, for a less morbid example, that's 79 times the calculated blast yield from all 3 stages of a fully fueled Saturn V rocket exploding on the pad together. All of that from 1 gram of antimatter and 1 gram of matter. Now, we have been able to produce antimatter in very small quantities. It's made using particle accelerators and particle decelerators, such as those operated by CERN. The total amount of antimatter ever produced by humans is less than 10 nanograms. Now, there's 1 billion nanograms in 1 gram. Now, some current estimates put it around $62 trillion to produce 1 gram of antimatter. Then you have to build a containment vessel, which is no easy feat, as the antimatter will want to react with any matter it touches, including the air. So it has to be contained in a perfect vacuum, suspended by a strong electric field. If something were to fail with this containment vessel, boom, 42 kiloton explosion. So the stakes are pretty high, to say the least. Now, as for the potential for antimatter high-speed space travel though, an antimatter propulsion system has a maximum theoretical speed of around 90% of light speed. And getting to this speed would, however, require 40.5 kilograms of antimatter, so 40,500 grams at $62 trillion each gram. And then you can double that because we have to be able to slow down at the other end. Now, I'm not going to do the math on that one, but it's safe to say it's beyond any amount of money that has ever existed in human history by several orders of magnitude. I am encouraged by the fact that this is theoretically possible in that we know how it works and pretty much how we do it. It's not like a warp engine, which is still well and truly relegated to the realm of science fiction. So maybe in 100 years, we'll have cracked this one. Who knows? What do you think? Let me know in the comments. As I said earlier, particularly for the experimental forms of propulsion, there's a really wide range of numbers on this stuff, so I've tried to be pretty conservative and take the middle road on my approach. I did my best anyway. Now, if you think I've missed some game-changing, critical experimental propulsion system, please let me know. I know I missed a couple of similar forms of propulsion to the ones that we discussed, but this video already ballooned out way more than I anticipated, so I had to make some cuts. But let me know anyway. I'd be keen to chat about it in the comments. Thanks for watching. Look, I know this one got pretty info dense, but I hope you enjoyed this as a thought experiment. I actually really enjoyed doing the research and even the math on this one, so I hope you got something out of it. Now, if you did, hit that subscribe button for me, and maybe while you're there, hit the like button as well. It helps me out and it really keeps me motivated to keep making these videos. Anyway, that's mission complete for me. Thanks for tuning in, and I'll see you next time.